So you are from?
I am working as a laboratory analyst in Numoligo Refinery Limited.
Okay. Okay, let me share the screen. Okay, is it visible?
Yes, sir.
Okay. So let us start. So today, uh, I will first discuss Carnot engine or Carnot cycle. Then we will solve related questions regarding Carnot cycle. Then, after solving the questions from Carnot cycle, we'll discuss about the Clausius-Clapeyron equations, and also regarding problems regarding Clausius-Clapeyron equation we will solve. And after that, we will solve various problem of like fugacity coefficient, and rather as discussed in the this week in the video lectures regarding that. Just I want to discuss the Carnot cycle because Carnot cycle was not discussed in the lecture videos, but it is still relevant and important. That's why I thought that briefly we can first discuss and also solve few questions regarding Carnot cycle. Okay, so let me start with. Okay, so first we will discuss Carnot cycle. Then we will solve the questions regarding the Carnot cycle. Okay. Okay. So Carnot cycle is basically a engine, means a cycle designed by Carnot which can serve the purpose of a engine. Okay, what engine basically do in we are very much familiar with the engines, right? Because engines are basically used to perform works. Okay, so in that perspective, Carnot cycle is an ideal engine. We can say this is an ideal engine, and the efficiency of Carnot cycle is maximum. Among all theoretical engine, there are lots of engine. Carnot auto engine are there based on auto cycle, and other engines are there. Stirling engines are there, but among these all engine, Carnot cycle or Carnot engine, the same thing. Are this engine have basically performs the efficiency of this engine is maximum, theoretically bound. So maximum efficiency of Carnot can be provided by any engine. So that is the Carnot engine. So first we will this involves very basic thermodynamic steps. So it's very easy to understand, but just we have to understand first theoretical model. Let's say two reservoirs are there, two baths are there. One is hot bath, another one is cold bath, we know. So let this is hot bath having the temperature TH, and this is cold bath having the temperature T. Cold or TL, H for higher temperature, L for lower temperature. Okay, now if you join these two reservoir to baths, this will act as source, and this will act as sink. Source means heat will flow from the this reservoir, and sink means the heat will flow to that reservoir. Okay. So now let's say we are adding this to reservoir through a engine. This engine is basically the Carnot engine. So how this Carnot engine design? So that we have to understand first. Carnot engine basically involve a ideal gas because it's the ideal engine. So here ideal gas is filled. So there are ideal gas. Now using this ideal gas, we can perform various thermodynamical process that we have to understand. Let's say just draw these steps, then we'll discuss. Like yes, P and V curve. So first there is ideal gas. So ideal gas will have some pressure and some volume. We know. Okay. So let's say there is this is the pressure and this is the volume of that ideal gas. Any P1, V1. We are starting ideal gas with any P1, V1. Now we just isothermally expand. Isothermally expand ideal gas. So if you expand isothermally, you know that temperature will constant, but pressure and volume will change. So let's say up to this point, it changes. So this is now P2, V2. Okay. After expanding isothermally, let next the gas expand adiabatically to P3, V3. Adiabatically means there will be no heat exchange with the reserve with the surroundings. So now first P1, V1 to P2, V2, then we allow to expand that gas adiabatically from P2, V2 to P3, V3. Now we'll compress again. If you compress again, now we'll compress isothermally from P2, V2 to let's say P4, V4. Yes, P4, V4. Now at last step, we'll again go back to P1, V1 by adiabatic cooling. So basically there are four steps involved. Let me, first one is isothermal expansion. Next is adiabatic expansion, isothermal cooling, and adiabatic cooling or compression. C for cooling, not cooling, for compression. So there are four steps. N- Let me define also the name. This is the state A, state B, state C, state D. So overall cycle is running between A to B to C to D. This is a cyclic process. Okay. So this is overall our mechanism, the steps involved. So now for first step, this is isothermal expansion. Isothermal expansion will be performed at a constant temperature. Let's say this is the temperature of high this TH higher temperature reservoir. It is part going in pH, pH, and this is at TL. Now we can solve. We can not we can easily understand the Carnot engine. Okay. So step by step, if you go through, probably this Carnot engine already studied in class 2 level, but again I'm discussing. Let first is AB. Path AB. This is actually isothermal expansion. Isothermal reversible expansion, to be more precise. Okay. So now we know for isothermal reversible process, the formula of the work done, because for this expansion from P1, V1 to P2, V2, we have to do some work done. So here we are, let me change the color. Yes, here some heat is given Q1 and we are getting some work W1, because for isothermal process we know that du is equal to d cross q plus d cross w. This is valid. So q and w both are there, so that's why we have to, for expansion, you can understand when expansion will occur, when you will give the heat, then the gas will expand, right? So that's why we are giving Q1 amount of heat and the gas is expanding, and due to that expansion, W1 amount of work done is occurring. So Q1 heat is given and W1 work done we are receiving as output. Okay. Now next is adiabatic reversible expansion. Now for adiabatic expansion we know that Q2 is 0 because in adiabatic case no heat exchange is occurring with the surroundings, and the output will be there some W2 due to change of internal energy. Okay. Uh, Now for the third case here, compression, isothermal compression is occurring. That means we are we are giving the work. That's why it is compressing. So now here we are giving W2, not W2, W3, and we are getting heat Q3. Because for compression case, isothermal compression, we compress, basically we compress the system, and due to that compression, uh, internal energy increase and also some amount of heat is exchanged with the surroundings. Okay. And for adiabatic case, again we are giving work, but here also there will be no change of heat. So this is total case, this picture. So now for isothermal reversible process, then what will be the, for first case, what will be the heat and work that we have to calculate. This we know basically that W will be, so W1 will be nRT ln V2 by V1. What is T here? TH ln V2 by V1. Similarly, Q1 will be nRT ln V2 by V1. Why? Because this is isothermal process and reversible process for ideal gas. Everything is there. So for ideal gas, we know that du will be 0 for isothermal process. So we can write, if du is 0, then d cross w equals to, basically these are d cross w. We are just writing in terms of w or q, but this is basically d cross w or d cross q. So we can think like that. This is du plus q plus w in this form. Then q will be equals to minus w, like this. Okay. So in that way there will be a minus sign. Okay. So this is isothermal reversible expansion. Next path is, okay, next is B to C. This is adiabatic reversible expansion. So what will be, here also you have to calculate the W. Now for adiabatic process, du is equal to, again you can think like this. Here q is 0, so du will be essentially the W. From here we can calculate, and we know that du is basically CVDT. So from there we can calculate W, that CV. So d, so here we can write that W. Is there any doubt? Then you can ask me. Just like here, you can prove like this, that du is 0. So q, d cross q equals to minus d cross w, and it is basically minus pdp. So d cross w is basically pdp. So if you integrate it from v1 to v2, then you can obtain that w equals to nr, because p, what is p? P is pv equal to nRT. So PV equal to nRT means P equal to nRT by V. So if you put it here, then you can obtain nRT by V. So now after doing the integration, you will obtain that nRT ln V2 by V1, that I have just written here, nRT ln V2 by V1. And now if you put it nRT ln V2 by V1 here, then Q you can also obtain. Just it is related to the minus sign. In that way, you can uh, understand how the W work can be calculated. Here also, du equals to, you can write d cross q plus d cross w. If this is the case, then here this is 0 and this is CVDT for ideal gas. You can write it. So now d cross w will be CVDT. It's just you can integrate both sides. Then w will be CV del t. And what is del t? So w2 will be CV del t. Del t is H minus TL, because we are changing the temperature. Here the temperature is changing because, understand, here for this, for first step A to B is occurring at TH, higher temperature, but this step is occurring at TL, lower temperature. So basically the temperature, this is isothermal process A to B. C to D is also isothermal, so temperature is changing due to B to C process, and it should be changing from TH to TL. So it is TL minus TH. Okay, so this is the W. Okay, now this is the BC is there now, and here the Q2 is 0. Third step, third step is C2D. This is again isothermal reversible compression. For that, similarly, here the formula is ready. Just we have to use this formula W3. What will be W3? NR. What is T here? TL. This process TL ln V2 by V1. What is V2 by V1 means? V final by V initial. Here, what is V final? V final is V4 and V initial is V3. So just we have to input here V4 by V3. Okay. And what will be Q3? Just minus NR TL ln V4 by V3. Now the fourth step is D2A. So it's a totally cyclic process. It started from A and it ends at the point A. So here the W4, what will be W4? Again, it will be CVDT. So CV dt is here TH minus TL. Similarly, here the temperature was TL for this case, and here the TH. So due to that process D2A, the temperature changes from TL to TH. So this will be CVTH minus TL. So, and also Q4 is 0. Okay, so this is our overall cyclic process. So now we have to calculate the uh, what will be overall output of work and the heat that we have to calculate. Then we can calculate efficiency, everything. I will come into that. But first we have to calculate this one. Okay. So now what will be W? Total W. W1 plus W2 plus W3 plus W4. So just you have to write it. We can see here that W2 and W4 same, just with opposite sign. So it will cancel each other. So it will cancel each other. So W1 plus W3. So it is NR TH ln V2 by V1 plus NR TL ln V4 by V3. We have to calculate this. So now we can, how we can calculate? For that we have to remember our basic thermodynamics first or second classes. Just we know that for adiabatic process, P V to the power gamma minus 1 is constant for adiabatic reversible process, right? For adiabatic reversible process. So here there are two steps. This step B to C and A to D, D to A. These both both lines are basically representing the adiabatic processes. So for two lines, we can write that for B to C, what we can write that TH V2 gamma minus 1 equals to TL V3 gamma minus 1, because the temperature is changing from TH to TL and volume is changing from V2 to V3 here. So it's better to write also here the temperature coordinate as well. Then it will be more clear. Here the temperature is TH. Here also the temperature is TH. Here the temperature is TL. Here the temperature is TL. Now it's okay. It's more clear. Okay. So now if you use this formula, then you can write that TH by TL is essentially be the V3 by V2 to the power gamma minus 1. Now, for another stroke of the derivative process, this is D2A. So, if this is D2A, for D2A, it will be TL is the temperature here. Just look at TL and volume is V4 and TH and volume is V1. So, V4 gamma minus 1, TH V1 gamma minus 1. So again we can write TH by TL is essentially be the V4 by V1 to the power gamma minus 1. If you equate, so what we can write that V3 by V2 gamma minus 1 essentially equals to V4 by V1 gamma minus 1. So V3 by V2 is essentially equals to V4 by V1. Okay. So if this is the case, then you can write it here also. V2 by V1 is V3 by V4. Okay. If they're in doubt, you can ask me. And now we'll again proceed. Okay. So now if this is the case, just we have to now calculate the W. What is W? NR TH ln V2 by V1 plus NR TL ln V3. What is V4 by V3? Okay. So it is NR TH ln V2 by V1 minus NR TA ln this V3 by V4. So what is V3 by V4? It is again equals to V2 by V1. Just write it. So it will be NR TH minus TL ln V2 by V1. So now V2 greater than V1, TH greater than TL. So essentially W is greater than 0. So we are getting a work done. Okay. So this is what due to this overall force stroke, due to this cycle, we are getting W amount of work done. That is a non-zero work done, and that is proof. Okay. So now we have to calculate the efficiency. What is happening? That means due to that cycle, that due to this cycle, if you look at carefully, we are getting total W amount of work done, which is some NRTH minus TL ln V2 by V1, and you are giving some amount of heat. What is the amount of heat? Q1 plus Q2 plus Q3 plus Q4. This amount of heat is no, this amount of heat is not given. What amount of heat is given? Q1 plus Q2. Q3 and Q4 you are not giving. This amount of heat you are getting. Q3 and though Q4 and Q2 is 0, so you can say that Q1 amount of heat. So in this engine, you can think like that. Just you can think like that. You are giving Q1 amount of heat, and you are getting Q2 amount, Q3 amount of heat, and W amount of total W amount of work. So this is you are getting. Okay, due to that engine, while performing in this engine, you are getting this. So using this engine, using this cycle, what you can do some work. Means if you have a Carnot engine, if you have a Carnot cycle, if you give some amount of heat, then it will perform some work. Okay, that is the basic definition of engine. It can perform work by using the heat. Okay, so that's why this Carnot cycle is called the Carnot engine due to this performance. Now you can calculate the efficiency of the engine. Efficiency of the engine. Don't know the spelling is correct or not. So, please. It's represented by gamma. Sorry. How it will be defined? It's easy. It amount of work done you are getting and amount of heat you have given. So it should be W by Q1. So W you know NR TH minus TL ln V2 by V1. Okay. This amount of work you are getting, and what amount of heat you have given? Q1 amount of heat you have given, which is nRT ln V2 by V1. nRT ln V2 by V1. Also minus sign was there, but we are interested just the magnitude. We have to calculate the efficiency. Minus sign was indicating that you are giving the heat. Okay, so that's why we are just using this. Okay, so if you use this, then essentially this will cancel. So it is TH minus TL divided by TH. So this will be the efficiency of the Carnot engine. Okay, so basically here the mod is used. You can think like that. If there is any doubt, then you can think like that. Okay, So TH minus TL by TH, this is the efficiency. And also you can rewrite the efficiency like this as well, 1 minus TL by TH. So essentially TL is always less than TH, always less than TH. So TL by TH is always be less than 1. So that means eta is always greater than 0. So eta is greater than 0 always. Greater when it will equals to 0, if TL equals to TH, then only it will be equals to 0. So it is bounded that eta is, and it's also be it is less. So better to write it. So this is basically it can't be if when it will be 1. If it is 1, then obviously TL and TH, this ratio. If TL is 0, basically, then it will be 1, right? But TL is 0 means you can understand that it is the minus 273 Kelvin. Okay, so this is the bound of efficiency. Okay, now if anything left, guys already discussed. Okay, so basically that's why here minus sign is given. You can think like that. No, it's okay. It's okay. It's okay. No minus sign is there. TH minus TL. It's okay. Okay. Now, yes, one factor we have to understand. Then we will do some problems. One thing you can also think like this: if pH goes to infinity, then also eta goes to 1. Means when pH is very, very, very greater than TA, then we can think that efficiency will be 1. Okay. So another one thing is there, that is coefficient of performance. This is represented by beta. Okay. So how the beta is defined? Beta is defined in right, just beta is the, okay, first definition. What is the definition of coefficient of performance? This is the ratio of heat transfer from a lower temperature to higher temperature to the work done machine to cause some output work. That is okay. In simpler language, you can think like that: the how much amount of heat is transferred. That is, we know that heat is transferred is, if you look at the cycle here, going into that, okay, here Q1. Okay, and there is also one heat is Q3. Q3 is also, but Q3 amount of heat you are receiving. You are receiving Q3 amount of heat. So you can write it. Okay, it is actually Q1 divided by, okay. So now if you calculate it, what will be Q1 divided by W? W you have already calculated. So now, okay, one more thing here we have to discuss. I forget it. There is another form. You can write it as, what is W? W was W1 plus W2. So you can write it like Q1 minus Q3 divided by Q1, like this. Okay, so it is basically Q1 plus Q3 by Q1 with a minus sign. You can think like that way also. Okay. Okay, this is Q1 by H. Now you can also calculate this beta in terms of TL and TH. So if you calculate beta in terms of TL of TH, you will obtain that beta will be probably, I'm not sure, TH divided by TH minus TL. I think it should be. Just its opposite, Th minus TL. Yes, Th minus TL, and this is T. No, I think there is some 1 minute. Let me check everything is correct or not. Yes. No. Let me do it explicitly. Then probably there will be no due to this shape jump. It is actually Q3. What was Q3? Q3 was NR, P, L, ln V4 by V3. And V4 by V3 is essentially equals to V1 by V2. So it is V1 by V2. And there was a minus sign. Uh, and it is NR PH minus TL V2 by V1. So you can absorb this and you can write, yes, PH minus TL.
Yes,
Yes,
Mr.
yes.
In the calculations of efficiency of engine, Carnot engine,
Mm.
we have the ratio of heat work divided by the heat supplied.
It's supplied. Here it is not.
Overall,
Yes, yes. You first you finish.
uh, again we are getting some heat also from the cycle. That is
Yes.
Q2 amount of heat is known. The Q2 amount of heat is not considered
Q3
in
amount
the
of heat. Q3 amount of heat.
calculation. Q7. Yes.
Huh. Yes, that is not
Uh,
involved. Let's say you can think like this. You have a machine, any machine you can have. Let's say using that machine, you can on a fan like this. You can or you can think like a train engine. Train engine you have seen, right? So what happens? Train engine basically do work, perform work. So for that work, you are supplying a heat that is Q1. So Q1 heat you are giving, and that engine is doing a work. The work amount is W, but due to that work, the engine is also getting heated. Just you can think your mobile phone. Mobile phones are doing performing while performing the mobile phone also warms, right? It gains heat. That heat is
yes.
Q3. That heat is
Yes.
all
Yes.
emitting. You that is called basically the waste heat. Okay, waste
Waste
heat
heat.
means you can't utilize that heat. If you utilize that heat, then it will be great. Okay,
Yeah.
that's why
Yes. Yes.
this coefficient of performance is important because it says that here you can think that if eta how much eta will be the large value of eta implies that the efficiency is better of that engine is good enough.
Mm.
Similarly, the small value of beta is also indicating that the coefficient of performance is better. Okay, that's the
Yes.
reverse one because it says that how much the waste heat is less, beta is less. So that is important. That's why beta is carrying that term, Q3 term.
Okay, sir.
So now in the frontier research, you can think like that. This waste heat management, you must be heard about. This waste heat is very important to manage. Then only the efficiency will be or more larger. So that is also important. And this waste heat is very important for the nanoscale devices, just like your mobile transistor. Okay, but okay. So let us proceed. This is TL divided by TH minus TL. So now you can prove a relation. This is our first question. You can think that beta will be no eta will be 1 by beta plus 1. So you can think how if beta decreases, then eta increase. From this lesson, we'll prove this lesson here. So it's easy, I think. Let what is this is Th minus TL divided by Th, and beta is TL by Th minus TL. So just reverse 1 by eta. It will be Th minus TL. If it is 1 by eta, then and you can think like that. Then 1 by eta minus beta, it is th by th minus tl minus th minus tl. So it is 1. So 1 by eta essentially be 1 plus beta. So eta is 1 by 1 plus beta. Okay. Also you can write this way as well. 1 minus eta by eta. The same thing. Okay, this is the first question. Now we have to discuss some question. First is the plots. Plots of Carnot cycle with respect to first one is H versus S, second one is U versus S, and third one is T versus S with entropy basically. So you know this for stroke. Now we have to just plot with respect to that variable. Let me just copy it. Okay. So this is our, we know this Carnot cycle. Now if you solve the first one, H versus S. So we have to plot. H is enthalpy, S is entropy. Okay, we know. Now for A to B process, first we have to think that A to B process. A to B process is isothermal reversible expansion. For isothermal reversible expansion, du is 0 and dH is du plus PdV plus VdP. You can think like that. Also, you know that you can think in this way, dH is also function of pressure and temperature, right? So just like du, how we can get it? Du is actually function of volume and temperature. So you can write du is equal to del u partial derivative del u del vt dv plus del u del tv dt. Okay. For ideal gas, this is basically our CV. This is CVDT. And for ideal gas, this is 0. This is 0. So that's why for ideal gas we write CVDT. That's why for ideal gas the del U del VT is 0. When the temperature is constant, you can change volume, you can change pressure, anything you can change, but that change in internal energy will be 0. Similarly, here for dH you can write del H del Tp dt. This is basically Cp. So it's Cp dt and del H del Pt dp. This is also 0. So here also when temperature is constant, you can change pressure or temperature, the enthalpy will also be, change in enthalpy will also be 0. So dH will also be 0. But you can ask that we know that H is equal to U plus PV. So now if it is du plus PdV plus VdP, so if this is the case, then how you can say that du is 0, we can understand. When temperature is 0, there is no internal energy change, but how the enthalpy change will be 0. So that essentially means that VdP should be equals to PdV minus with a minus sign, then only it will be 0. So you can, you have to prove this. You can think like you can think how dH can be shown that dH should be 0 using this lesson. Okay, so here that for A to B, H is not changing, H is constant. Next is adiabatic expansion. For adiabatic expansion, what will happen? For adiabatic expansion, we know that for adiabatic process, d cross q is 0. And if d cross q is 0, then we know that d cross q is basically TdS. That means ds is 0. So if ds is 0, then entropy will not change. So for adiabatic, this is known to us that for adiabatic process, entropy change will be 0. So this should be like this. And again, similarly, for isothermal compression and for adiabatic compression. So this will be our Carnot cycle in terms of H and S. This was P and P, this is H and S. Okay. Now next one is US and TS. So similar, you no, this is okay, okay, okay. This is T and V, T and V, and this is U and T. So U and T for isothermal process, you will not change. For A to B, you will not change. This is isothermal expansion. Next is adiabatic expansion. Now for adiabatic expansion, temperature is not constant. You can see temperature is changing from TH to TL. So temperature is not constant. So temperature is what is happening? Temperature is increasing or decreasing. That we have to understand. This is, okay, okay. 1 minute. Okay. Mm, okay, okay. It's mistake. For fast process A to B. Sorry. For A to B, this is isothermal expansion, right? So for isothermal expansion, du is 0 and dt anyway is 0 because this is isothermal expansion. So for A to B, the point will not shifted. This is very important. This is very tricky. For isothermal expansion, the point A and point B will be the same in terms of U and T. Temperature is not changing. So state A, the temperature is TH and U is, let's say, U. And for B, it's also TH and U. It is not changing, so point will not move. So for isothermal expansion, the point A and B will be the same point. Let's say any point here, any point. This is A and this is B. The point is not changing for isothermal expansion. Now, when the adiabatic expansion is happening, for adiabatic expansion, the temperature is decreasing. Temperature is decreasing to TH to TL. So let's say here, this is TH, this is TL. Also, internal energy will also be decreased. So this is C and D. So this is the adiabatic expansion and the reverse one is the adiabatic compression. So this will be the graph. So it is very odd looking, I know, but this will be the graph. So first it's A point is this, A to B is this, A and B are the same point. Then it is going to C is the same point and C to D is the same point. Okay. So this will be the graph. And the next plot is T and V. So T and V. For first process, that is the isothermal process, so T will not be changed. T is fixed. This is isothermal process A to B. And next one is V is increasing. It is going to V2 to V3. We can see here. How we can understand that V2 and V3 is greater than V2 because it is expansion. And due to expansion, the volume increases. So it will go from V2 to V3. And again, it will be compressed isothermally, so temperature will not be changed. And this is the adiabatic compression. So this will be the in terms of P and V. Okay. So probably this type of question is done. Now some mathematical question if you want to solve, I can solve on how much question is there. Let's say this is very trivial. One difficult question. Let me. Okay. The next for ask that this is the third question, right? What percentage of PL of pH for a 10% efficiency. Means if you want to have 10% efficiency, that is eta, the percent of efficiency eta, 10% efficiency, it's given in percentage, okay? But we have calculated eta in fraction. This is a fractional quantity. This is a fractional quantity, as I discussed in general. So this is a fractional quantity, so we have to calculate in terms of fraction. 10% efficiency means it's eta is 0.1. So we want to eta 0.1, that means 1 minus TL by TH is 0.1. So essentially TL minus TH should be equals to 0.1. Oh, sorry, 0.9. It, okay. So now what percentage of TL of TH should have been? That means TL is 0.9 into TH. That means TL should be 90% of TH. Okay, okay. One more question, then we'll go to the Clausius part. Question is, a Carnot cycle operates on a temperature difference that is given, temperature difference of 2000 Kelvin, sorry, 200 Kelvin. One third of the heat absorbed from absorbed from this at T2 is discharged as waste heat. Just you are asking that this term also given in question. This type you have to understand what is the waste heat to the sink at T1. The cycle does 400 joule of work. It's a good question, I think. So calculate Q1, Q2, and T1. Q1, Q2, and T1. That you have to calculate. What is T2 and what is T1, you have to understand. Just read it. A Carnot cycle operates temperature 2000 Kelvin, means TH minus TL, as we understand. But here heat is absorbed from the cycle, one third amount of heat absorbed at T1. Oh, T2. Okay, then that means TH is here is equivalent to T2, because in our model heat was absorbed at TH. Here heat is absorbing at T2 and discharge is at T1. Okay, so TL is basically T1 here. So you can reframe the question like that. If you understand in our language, then it will be easier. Okay, so now they want to ask Q1 and Q2, basically Q2, it's Q3, it's Q3. Q2 is essentially 0. Okay, so this we have to calculate. TH is given, T2 is given. Now T1 means TL we have to find out. One third of heat absorbed from one third of heat. T2 and discharge as waste heat sink at T1. Okay, so let's say we don't know anything here. So the amount of heat absorbing, that is we know Q1 amount of heat basically absorbed, and Q3 amount of heat is going to the sink, and source is giving Q1 amount of heat. Now, one third amount of absorbed heat is discharged as waste heat. So Q3 is essentially Q1 by 3. Okay. So if Q3 is Q1 by 3, now what the cycle does, 400 joule of work. Okay. So W is given 400 joule. So this color is not good. So 4 W is given, that is 400 joule. So if W is 400 joule, then we know what is the W. W is basically Q1. Do it separately. It is NR TH minus TL ln V2 by V1. This is 400 joule. That is given. Efficiency we don't know here, but efficiency we can calculate, but that is not needed. That is not needed. W is given. Now we have to calculate Q1 and Q3. So Q1 we know that is minus NR TH ln V2 by V1. And Q3 that is also we know that is minus NR TL ln V4 by V3. And we know also that V4 by V3 is equal to V1 by V2. If I'm not wrong, V4 by V3 is equal to V1 by V2. Yes, so you can write it V1 by V2. Okay, so Q3 again, so Q3 is Q1 by 3. And you have to understand this is the mod values. Okay, we are not taking the direction. If you consider, then there will be a minus sign because Q3 amount of it is going to the sink. So in terms that is there will be a minus sign. So if you put it, so it will be minus NR TL ln V1 by V2 equals to minus NR TH by 3 ln V2 by V1. Okay, there will be no minus sign because there is a minus sign and it had another minus sign, so it will be no. Okay, so you can absorb this minus sign and you can reverse the ln, so this will be cancelled. NR will be cancelled. So it's clear that TH is equals to 3TL. It should be because TH is the higher temperature. So TH is equals to 3TL. This is we have find out. Now we have to find out what is the Q1 and Q3. Okay, what is the Q1 and Q3? And del T is given. Del T is 200 Kelvin. That means TH minus TL is 200 Kelvin. If this is, then 3TL minus TL is 200 Kelvin. So TL is essentially be the 100 Kelvin and TH should be then 300 Kelvin. So temperature we have identified. Now we have to identify the Q1 and Q1 and Q3. So how you can identify that? Uh, One formula you can use, that eta is basically TH minus TL by TH, that was equals to Q1 plus Q3 divided by uh, Q1, like this. Okay, so if you use this formula, then you can write it, then TH minus TL, that is 200 and TH is 300, equals to 1 plus Q3 by Q1, and Q3 by Q1, okay, that is also known, that will not help essentially. Okay, no, we have to, okay, no, just think. W we know. Okay. So now again focus on W. What was W here? W is W1 plus W2 plus W3 plus W4. right? And if you remember that W2 and W4 cancel out, so W and W3 was there. So W was basically W1 plus W3. That means Q1 plus Q3 with a minus sign. That is given 400 joule. That is given 400 joule. And you know that Q1 is Q3 by 3. No, Q3 is Q1 by 3 with a minus sign. So if you put it, that means Q1 is basically 3 into minus 3. So if you put it here, then you obtain 4Q1 is basically 400 joule. If you, 1 minute, let me check. No, this is Q1. It says basically minus 3Q3 plus Q3. This is, here is another minus sign. So minus of minus 2Q3 is 400 joule. Yes. So 2Q3 is 400 joule. So Q3 should be 200 joule. It is heat. Okay. Now Q1 is 600 joule. So mine, there will be, sign will be there related to Q1 and Q3, but we have to interested in the value. Q1 is the heat. This is the heat entering from the source to the system or engine, and this is the heat emitting from engine to the sink. Okay, and now we'll go to the Clausius-Clapeyron part, or Clausius then Clapeyron. Yes.
Can we explain Carnot refrigerator is not required
No, you
in
can
this course,
now
I
Carnot
think.
yes, yes. If you think the Carnot refrigerator, that can not Carnot refrigerator, just normal refrigerator. Refrigerator is just the reverse. What happens here? What is happening? You are giving the heat, and it will performing a work. In that case, it will,
Yeah.
if you reverse the cycle, now then you see that it will you have to give a work, and it will perform the heat. Means that it will emit the heat. What happened in refrigerator, that heat is going from TL to TH, means higher temperature, lower temperature to higher temperature. That is not our intuitive, right? We know from thermodynamics that heat should go from higher temperature to lower temperature. But to make heat flow from lower temperature to higher temperature, that means you want Q negative. For Q, you have to just give some amount of work here. So if you perform some work, then it will go from TL to TH. That is just refrigerator, the reverse one. Here you can, what you can see here, that Q1 amount of heat, this amount of heat is basically given by TH, and Q3 amount of heat is going to TL. So TH is
Yes.
giving Q1 amount of heat, and TL is absorbing Q3 amount of heat, and the difference between this heat Q3 and Q1, this amount of heat is basically converted to the work that is done by the Carnot engine. But in refrigerator, so you can just visualize this photo, it will be just clear. That means this is giving a Q1 amount of heat, Q3 amount of heat is going there, and rest amount of heat is performing the work. Just refrigerator, you just reverse the sign. You have to give Q3, W amount of heat, a work, and Q3 amount of heat will come from TL and going to the Q1. Just like this. This will be the just refrigerator.
Okay, sir.
Okay. Um, you can solve like the cycle. You can try. If there is any problem, yeah, we can discuss in next class also. The cycle will be similar cycle, just with a reverse stroke. Reverse. This refrigerator is basically we daily we use in our AC, in our refrigerator, fridge. The same procedure. Heat is going from lower temperature to higher temperature just by using the electrical work. For that we have to do electrical work. You can try by your own. If there is any problem, we can discuss the refrigerator part as well. Okay. So now the Clausius Clapeyron, that one. Okay. Please. Yes, yes, yes. Okay. Here also we'll first understand the Clapeyron equation, Clausius Clapeyron, then we'll go to the question. There are few questions regarding this, and this Clausius Clapeyron equation is very important to solve the numerical problems. Lots of numerical problem asked. So we know the Clausius equation we know. Okay, we know means in class it was derived that dp basically del h by d del v into dt, or you can write dp dt d del v. This del h, del v, these all are not. This del h is basically del h transformation. Del v is also the del v transformation, means we are changing a phase from P1 to P2. Let's say liquid to solid, or liquid to gas, or gas to solid, or solid to gas, any two phases. In between phase transition, this classical Clausius Clapeyron equation is basically valid for phase transition. Okay, so del H transition, del V transition. This equation was known. This you can derive by using thermodynamical law, and in class it was discussed. So now we have to understand what is the Clausius Clapeyron equation. This equation is Clausius equation. Clausius Clapeyron equation, just we have to put some condition in it. Consider the transition for solid to gas or liquid to gas. Why these two transition we are considering? For solid to gas, that V del V is basically Vg minus Vs, and here the del V is Vg minus VL. Both are equivalent to Vg because the volume of gas is much more higher compared to solid or liquid, volume of solid or volume of liquid. So you can approximate in this way, and it is a good approximation, you can say. So you can write the del V is essentially Vg, essentially nRT by P. You can write it. So now if you put it here, so del P del T, what will be del P del T? Del H by T del V. So del H by T del V. So del H by T, what is del V? nRT by P. So it is del H T by nR T square. Yes, B by T square. Yeah. Okay, this is so you can write dP by P equals to del H by nR T square dt. Now you can integrate from T1 to T2, P1 to P2. Okay, so if you integrate, it will be ln P2 by P1 dH nr. This will be dt by T square. Here we are considering del H is not a function of temperature. The how you can think that for phase transition, uh, the phase transition basically occurs in a constant temperature, right? So for that, let's say water, the solid ice is melting to the water. This phase transition will occur at 0 degree centigrade. So for that, the del H should not be the function of that temperature. So grossly, you can think like that. It's not that much straightforward, but okay. So it is del T by T square. So what will be del T? So it is del H by nr minus 1 by T, T1 to T2. So it will be del H by NR 1 by T2. Yes. Okay. So ln P2 by P1 is minus del H by NR 1 by T. So this is, so this equation is very important. This is basically Clausius Clapeyron equation. So further we can write that. So P2 by P1 is e to the power minus del H by NR this this we can write. Okay, so this is another form. Okay, so now we have to just change cross check this application. First is liquid to vapor or gas. So for liquid to vapor, okay, no, this one, these things are done in the class, so it's not important. So let us move to the problems. Fifth problem, I think, for today's class, or fifth or fourth problem. The specific volume, let me first write the problem. Okay, so specific volume of liquid water is 1.001 ml g to the power minus 1, and that of ice is 1.0907 ml g to the power minus 1 at 0 degree centigrade. With the heat of fusion of ice at this temperature is the rate of change ice with pressure will be. Okay. So specific volume of liquid water is given. For ice is also given. So we can first just you can think that the volume is increasing. Okay. Next is at 0 degree we know if the heat of fusion is given of ice is this. This is the heat of fusion. The rate of change of melting point. Okay. Del T. This means the rate of change of melting point means that we want to have the del T with press. We have to calculate. We have to calculate means dt dp. Dt dp we have to calculate, but we can also calculate dp dt. Just again we have to reverse it. These we can calculate using Clausius-Clapeyron equation. Okay, so what is dPdt? Del H by d del V. We have to use this formula here because this transition is occurring between uh, liquid and solid. We can't use the Clausius-Clapeyron one. You have to use the Clausius equation. Okay, so now if you use the Clausius equation, so it will be del H by T, and this will be V. Del V we have to understand. Now del V, it is changing from mm, heat of fusion. What? Fusion of ice. Okay, okay. That means ice is melting to the uh, liquid. So it is VL minus VS. That means solid is changing to liquid. Okay. So at temperature is 0 degree centigrade, not Kelvin. If it is 0 degree centigrade, that means it is 273 Kelvin. And VL minus VS. VL minus VS is given. Okay, for before that you can just reverse it. This is asked, right? So you can reverse it. So T is 273 Kelvin. VL minus VS, that is also given. VL is 1.001 and this is 1.0907 ml. And del H. Del H is also given. What is del H? 333 point heat of fusion, that is the del H here. It is joule per gram. Okay. So this will be cancelled out. Okay, so just you have to calculate this. Let me calculate. Okay, the first is this difference 0.001 minus 1.7. So this is 273 into minus 0.0897 divided by 333.88. Okay, what will be the unit? Unit will be degree because this is Kelvin. Okay, let me make it Kelvin. Kelvin ATM inverse. Okay, so now if you multiplied with 273 and divided with 333.073. Okay, so this is del T del PP. So question is not very difficult, but the language was tricky a little bit. Okay, now for the next question. Next question. Question number 5. The vapor pressure of decay is 10 torr at and 40 torr at 150.6 degrees centigrade. The del is vaporization, okay, at 100 degree centigrade will be. Okay, So vapor pressure of decant is given at 10 torr. 10 torr it is this one. 10, okay, and 40 torr. Okay, okay. So del is vaporization there. So del H, that means vaporization means liquid to gas. Okay. So del H essentially be here equivalent to del H is basically del G Hg minus HL. So we can think del H, we know del G is del H plus T del S. For transformation, okay, for transformation, it's the equilibrium process. We know when the phase is changing, that will occurs in a equilibrium, right? So that's why we write like this. Now for equilibrium process, del G should be 0. So del H transformation is equals to this. Okay. Minus T del S minus T. Okay. So now we have to just calculate del H and we have to then divide it with T. So del H we can calculate using Clausius-Clapeyron equation here. Why Clausius-Clapeyron equation? Because it is liquid to gas. So directly we can use the Clausius-Clapeyron equation. So what does Clausius-Clapeyron equation says? That ln P2 by P1 del H by nr equals to minus H by nr 1 by T2 minus T1. Let me check. Yes. Okay. So ln, what is P2? First P1. Any you can think P1 or P2, that does not matter. Here for 10 it's 55.7. So P1 and P2. P1 is 10 and P2 is 40. So it will be 40 by 10. Okay, del H we have to identify it. NR we know. Uh, okay, next is temperature. Temperature is 100 and 1 minute. Okay, okay, no. It is 55.7 and 150.6. So P1 is 273 plus 55.7. So it is essentially be the 328.7 degree Kelvin, not degree, just Kelvin, and T2 will be 273 plus 150.6. It is this. So it will be T1 minus T2 by T1 T2. So it is ln4. This is okay, ln4. If you absorb this minus sign, then it will be T2 minus T1 divided by T2. Okay. This is 400 torr. 400, not just now. We have to calculate del H here. Del H will be, this will be now ln 440 equals to del H by nr, and this will be T2 minus T1 is 20. Just have to subtraction. What will be 423.6 minus, so it is 94.9 divided by T1 into T2. Okay, so this is an nr. n is 1 anyway. How do we know n is 1? Because when anything is not given, you have to understand this is for 1 mole. And R 8.314. So just do it. So del H will be 8.314 into 423.6 328.7 into ln 40 divided by 94.9. So it is, let me do 8.314 into 423.6 into 3287 into ln 40. So it's huge. So it will be, no, it will be then divided by 94.9. So it is divided by 94.9. Okay, so it is 44998 this joule. Okay, this is the del H. So now we can calculate the del S. Del S just del H by T. So 44998 joule divided by T. They have asked for 100 degree centigrade. So 373. So it is 120.63 joule per Kelvin. Okay. So let us do one more question regarding this Clausius Clapeyron, then we can go to the next part. This question is good. Okay. The sixth question. Calculate change in temperature of boiling water when the pressure is increased by 27.12 millimeter of Hg. The normal boiling point of water at 1 atm is 100 degree. We know this. Okay. What is given? Given that latent heat of steam, this is also we know, and the specific volume of steam, that is also given, that is okay. So this information we know. Now we have to calculate the change in temperature of boiling water, means del T. When the pressure is increased, that means del T del P. Okay. So we have to just find del T del P, then we have to just identify the del T. That is important here, del T. Okay. So now we have to use here the boiling water, means it is changing from liquid to, it is changing from liquid to vapor. So we can use the Clausius Clapeyron equation here. What is the Clausius Clapeyron, or in general Um, no, we can use Clausius-Clapeyron also, but still, let us start with del P del T is del H by T del P. This is known to us. Okay, let me. Pressure is increased by this amount of Hg. Okay, okay. 1 atm. Okay, 100 degrees given. 100 degrees is okay. At 1 atm, the water boils at, we know, water to steam at 100 degree. It at 1 atm it vaporize at 100 degree centigrade or 270 to 373 degree Kelvin. Now this is increased. The pressure increased 27.12. That means now it is 1 to what? Millimeter of Hg. 1 atm is 760 millimeter of Hg. Now it is increased 760 plus 27.12 millimeter of Hg. Under this condition, they are asking the temperature on which the water will be boiled to the steam. Let us try. Okay. What is the Clausius-Clapeyron equation? ln P2 by P1 equals to minus del H by nr 1 by T2 minus 1 by T1. So they are asking about T2. T2 and the latent heat of steam. Latent heat of steam is given, that is 573, that is the del H per gram for 1 gram, and specific volume they have also given. Why they have given a specific volume that is needed here? Okay, okay, here we, should we ignore that? 1 minute. Okay, let us start using dp. If needed, then we can also derive that one. P del V. So it can be written as del H divided by V2 minus V1 1 by T. So dq will be V2 minus V1 divided by del H into T into dp. Okay. So dp is given. What is dp? dp is 27.12 millimeter of Hg. Okay. Now equals to 27.12 divided by 760 atm. We need that because we know that for 760 millimeter of Hg is equals to 1 atm. So dp is known, and so dp will be 27.12 divided by 760. This is atm. Now this is the bar. Now this is the Newton per meter square. So if you calculate it, it will be, let me calculate, 27.12 to 0.01 into 10 to the power 5 divided by 760. So it is 3604.105 Newton per meter square. Now del H. Del H is given per gram. We are considering 1 gram. So for 1 gram, it is just 537 calorie. Now if you want to have in joule, we have to multiply it with 4.18. So it is 224466 joule del H. And we have to need this V2 minus V1. Now V1 is 1 cc. 1 centimeter cube, and V2 is given, that is 74 centimeter cube. Okay. V1 is the volume of the water, that is 1 centimeter cube, because we are considering that for 1 gram. 1 gram of water, for water, the density is 1, right? So 1 gram of water occupies 1 centimeter cube of volume. So V1 is 1 centimeter cube. We can use the, why we didn't use the Clausius-Clapeyron equation? Because in Clausius-Clapeyron equation, we are not considering the volume of water, but here the volume of water is 1. We can ignore in terms of this, but still it is better to account that also. Okay, so now we have to convert it in meter cube. So just we have to multiply with 10 to the power minus 6 meter cube, all are in SI unit. So it is, okay, so del V. So del V will be V2 minus V1. So it is this, hence, what will be dt? So dt will be del V divided by del H into T into dP. Everything is known. So del V is 1673 into 10 to the power minus 6. T is 100 degree centigrade, means 373 Kelvin. dP is also known. dP is 3604, is 3605 or 4.105, and del H is also known, 537. Now if, no, not 537, it is 2244.66. 2244.66. So if you calculate it, what we will have, 1673 into 373 into 3604.105 divided by 2244.66. Okay, this one into 10 to the power minus 6. Okay, so divided by, okay, so it is 1.0019 Kelvin. So approximately you can write it 1 Kelvin. So this will be the dt. That means T2 will be U1 plus dt. So T1 was 373, so it will be 3. Okay. So now we are going to our next part, the fugacity part. Regarding question, we will solve. It will be our 7th question. Fugacity we know because it was discussed in class. Here we will understand it. Now we'll solve the question and not prove basically. Then it will be more clear for us, I think. Yes, and then we'll, mm, if time permits, then we'll solve another few questions. Okay, so we have to prove that first. This question has two parts. First is escaping tendency of real gas is less than ideal gas. We know that fugacity is basically a concept for real gases. For ideal gases, there is pressure. For real gases, we have just replaced pressure with the fugacity, and we can construct similar kind of equation. So it's a for real gases. For second one, escaping tendency at high pressure. This is for low pressure. This is for low to moderate pressure. Pressure of real gas is greater than ideal gas. So we have to prove that escaping tendency of real gas is less than ideal gas for it is ideal gas for moderate pressure or low pressure, but for high pressure it's reverse case. Okay, for that we have to use the obviously the fugacity part. So we know what was the definition of fugacity, everything we know that fugacity coefficient is basically f by p. If it is f by p, then RT ln gamma should be equals to 0 to p v real minus v ideal dp. So this is our fugacity equation. This gamma is fugacity. Yeah, gamma is coefficient, not fugacity. F is the fugacity. Okay. So now we can write it. Z is compressibility factor. Compressibility factor, which is defined as V real divided by V ideal. So we can write V is essentially Z into V ideal. If you put it, then ln, no, not ln, so RT ln gamma, that should be equals to integration 0 to P V minus V ideal, means Z into V ideal minus V ideal into dP. So 0 to P Z minus 1 V ideal into dP. Correct. This is the case. So now we know that V ideal is RT by P. This is correct. N is 1, considering N is 1, obviously. So this is RT by P. Hence, ln gamma will be 0 to P Z minus 1 dP by P. So this is the equation. So ln gamma is 0 to P Z minus 1 dP Z minus 1 by P dP. This is the fugacity equation, right? So we have to use this one. Okay. Now case 1 for the question 1 at low or moderate pressure. So low or moderate pressure, what happens? We have to think two cases, that ideal gas and real gas. Okay. So for ideal gas, there is no attraction, no repulsion. But in real gas, there is some attraction, there is some repulsion. But as the pressure are low or moderate, that means the molecules, gas molecules are close enough. So that's why the attraction is dominating. Okay. So their attraction at this condition, attraction is dominating over repulsion. When repulsion will dominate, uh, if the gas molecules are very closest to each other, very close to each other, then the repulsion will dominate. We have seen the Jones type of potential, right? It's looked like this. Here, this part is attractive part. If the distance is very close, then the repulsion will dominate. So there are two terms, repulsive term and the attractive term. In attractive term, there is to the power minus 3, and repulsive term there is to the power minus 6. So when the R is very less, the distance between two molecules, then the repulsive term will dominate. Otherwise, attractive term will dominate. So at lower moderate pressure, attractive term will dominate. So now we know the real gas equation, that means the Van der Waals gas equation. We have to consider that for Van der Waals gas, we know that for 1 mole, obviously, equals to RT. Here we know the first part, it comes from PV equals to nRT. A plus B square, this term was added due to count the attraction, and this B due to the repulsion. So here the attraction is dominating. So we have to just consider the first part. B we can neglect here. Here is the catch only. So we can write it in like this. Okay. So if you write it like this V is actually the ideal. Uh, so you can write it. So V ideal will be RT, or let's say PV plus A by V equals to RT. Hence, PV by RT plus A by RTV is 1. Now, uh, PV by RT basically is the Z. Why? Because RT essentially is PV ideal. So you can write it. This V is not ideal, so this is real. So it is just, you can write it. If there is no notation, that means the real. For ideal gas, there is notation of ID suffix. Um, suffix. So V by V ideal, and V by V ideal we know that is Z, compressibility factor. So it is 1 minus A by RTV. Now we have to just put it ln gamma. What was ln gamma? Ln gamma was integration 0 to P Z minus 1 by P into dP. So 0 to P Z minus 1 will be minus ARTV. So we can write it minus A by RTPV into dP like this. So it is minus 0 to P. This here everything is positive. Okay. So you can write it. So you can write it that so ln gamma is basically less than 1. Okay. So ln gamma is if less than 1. Oh, sorry, not less than 1, less than 0. Because this everything here is positive. So this part is greater than 0. There is a negative sign. So it is less than 0. Means gamma is less than 1. So if gamma is less than 1, that means f by p is less than 1. That f is greater than p. Sorry, less than p. Hence, here it's clear. F is the pressure for you can think like F is the pressure for the real gas and P is the pressure for the ideal gas. So this is less than. So uh, now you have to understand. So at lower moderate pressure, attraction dominates. Therefore, the force by which a molecule hits a container, that decreases. That means the force by pressure of real gas is less than P. Okay, so that's why the escaping tendency of real gas is less than. Escaping tendency means that the pressure. How if the pressure is much, that means the escaping tendency is much. So that means the escaping tendency is less. Pressure is basically represent the escaping tendency for real gas, and F, the fugacity, represent the escaping tendency for ideal gas. Okay, now the second part, at high temperature. So what will happen at high temperature? Obviously, the repulsion will dominate over attraction. So if that is the case, then this was our Van der Waals equation. Here we can ignore this part. So essentially, you can write this. So hence, PV by RT minus PB by RT equals to 0, not 0, 1. So this is again, similarly, this is Z equals to 1 plus PB by RT, or Z minus 1 is PB by RT. If this is the case, hence ln gamma, that will be integration 0 to P Z minus 1 by P dP. So it is 0 to P Z minus 1 is PB by RT by P means it's B by RT dP. So B by RT will be out from integration and this is dP. So we can write PB by RT. So gamma will be e to the power PB by RT at high temperature, means F will be P into e to the power PB by RT. So it's clear that F will be greater than P. Okay, so if F is greater than P means the escaping tendency is greater. Okay, okay, this is okay. Okay, now we have to check other questions regarding the fugacity. Is there any question? Let me check. Okay, I don't think so. This is okay. This was- One question is there, but this is very trivial question. Let us solve still. To the power BP by RT, so they ask that what is the question number 8. Question number 8, what is the free energy change accompanying the compression of one mole of a gas at 57 degrees centigrade from 25 to 200 atm. The fugacity of the gas at 57 degrees centigrade may be taken as 23 and 91 atm respectively at pressure 25, pressure of 25 and 200 atm. Okay, they have asked the free energy change, okay, of one mole of a gas 57 at 57 degree is changing from 25 to 2000 atm. So we know dg equal to VDP minus SDT. Temperature is constant, so this term will be 0. So we can write dg equals to VDP, right? Now, if you integrate it, then you will have that del G equals to V. This is for ideal gas. So PV equals to nRT we know, and we are taking for 1 mole of gas. So for 1 mole of gas, it should be the RT. So this will be integration RT by P into BP, P1 to P2. So RT ln P2 by P1, which is the del G for ideal gas. So if you calculate, then del G equals to RT ln, what is P2 and what is P1? P2 is 200 and P1 is 25. That means P2 by P1 is 200 by 25. So essentially it is RT ln 8. What will be RT ln 8? Let us calculate. R will be 8.314. T is 57. So T is 273 plus 57 is 330 into ln 8. So it will be 8.314 into 330 into 2 ln 8, it is 5705.19 joule. Okay, this is for ideal gas. Now for real gas, we know del G will be RT ln F2 by F1, the fugacity, and that is given to us, that is RT ln 91 by 23. So it will be 8.314 into 330 into ln 91 by 23. So if you calculate, then it will be 8.314 into 330 into ln 91 by 23. So it is 3773.479 joule. Okay, so we have calculated for both real gas and the ideal gas. Okay, so this was our question number 8. 9. Okay, write down the equations of changing various, this is also important, functions considering particle exchange is also occurring. Okay, this is our last question for today's class. So we know for particle exchange we have to consider that chemical potential part as well, right? So what is the definition of chemical potential? For ith species, mu I is defined like del G del Ni when other parameters are constant. Okay, so this is the case. So now we have to also means that we have to understand this first. We know before that dg was vdp minus sdt, right? If dg equal to vdp minus sdt, that means del g when dg at constant t and p, it should be 0. Constant t and p both will be 0, so it will be 0. But here we can see when there is a particle exchange between ith and jth particle and other particles, then there will be a chemical potential. So you can't write d is equal to vdp minus sdt. We have to again rewrite this equation. Still now, till now, what we have studied, we have what we have solved, these all are considering that there is no particle exchange. Okay, so now we have to write it. G is a function of temperature, pressure is okay, but other species as well. Let's say there are k species. So dg will be del g del tp, not p only, that n I, all ni, dt plus del g del pt ni plus del g del ni, pp constant, nj not equals to ni is constant, and dni sum over of all I is varying from 1 to k. So this will be the dg. Okay, so these things we know. This is minus s dt. Here, from here we can, this was known, right? Hence s is minus del g del tp, and v is del g del pt. So this is minus s dt plus, okay, here dp, v dp plus sum over I equals to 1 to k. This is mu I dni. So hence we can write dg equal to vdp minus sdt was there, but we have to now add sum over mu dn or mu I dni. This we have to add. This is for dg. We have to also calculate for others. First we have to start with, let's say if we are starting with h. What was h? dh. dg equals to dh minus tds minus sdt. Here, because we knew that h is equal to g equals to h minus ts. So dg is this. So vdp minus sdt plus mu I dni is equals to dh minus sdt minus tds. So this will be cancelled out. So we can write dh is essentially be vdp plus tds plus mu I dni. Okay, this is for dh. And now u, h is basically u plus pv, or we can write u is h minus pv. Hence du will be dh minus pdv minus vdp. If you put it, vdp will be cancelled out, so du will be pds minus pdv as mu I into dni. Okay, so this is for du. Any da, a, g, and a is left, right? A is Helmholtz free energy, and Helmholtz free energy is defined like u minus ts. So from Helmholtz free energy, you can also write. You can write from the our thermodynamic square as well. Let me see that. Okay. So in general, we can write it from all equation from above equations. What we can write that mu I is equals to del G del Ni Ep Nj not equals to Ni equals to del U del Ni Sv Nj not equals to Ni equals to del A del Ni. What will be there? Vt Nj not equals to Ni and del H del ni ps nj not equals to ni. One thing that you can show that dA will be vdt, I think. Okay, no. Okay, okay. du, dh, dg that are shown. So similarly, you can also dA you can also shown. So that is we'll discuss in next class. What will be that? No, let me there it is there, but okay, we can do it. dA d why we should not left it. Okay, what is the formula of dA? The dA is Helmholtz free energy, right? Okay, Helmholtz is U minus TS if I'm not wrong. 1 minute, let me check. Yes. So if it is the case, then dA will be du minus TdS minus SDT, and du we know this is, so it is TdS will be cancelled out. It will be minus SDT minus PdV plus sum over I mu I dni. It was easy, just okay. So from here you can also write this. Okay, so let me stop. If you have any question, you can ask.
Just one in the solution of question number 4,
Four
the calculation part. Calculation only the calculation part.
here, right? This problem?
Uh, yes.
Yes. Mm.
Here we are getting 1.001 and 1.0907 milligram
Yes.
ml per gram.
Yes. Gram inverse. Yes.
ml per. Uh,
Hmm.
Here ml is not converted to meter cube. Is it okay or anything?
No, it is milliliter, right? Milliliter. Liter means 1 liter means how much?
10
One decimeter.
kilograms?
1 decimeter cube,
Yes.
and milliliter will be 10 to the power minus 3 decimeter cube,
Yes.
right? So now you can convert it. It is 1 minute joule in meter, right? So 1 decimeter is 10 meter.
10 meter. Yes.
Mm. So if you put it here, so 10 to the power minus 3 decimeter cube is how much?
1 meter cube.
So that's why. So milliliter and meter cube is the same.
Okay. Thank you.
Okay. So okay. So let me stop screen sharing. Stop. Preventing. Okay. So now we can leave the session and we will meet again in next one.